The Big Bang Theory is the leading explanation for how the universe began. Simply put, it suggests that the universe as we know it started from a singular point of extreme heat and density, expanding and stretching out, first at unimaginable speeds, then at more measurable rates, over 13.7 billion years to the expanding universe we observe today. With the advent of James Webb, we now can peer back in time, approaching as close as possible to the moment of the universe's birth. While previously limited technology prevented astronomers from directly witnessing the universe's inception, and much of our understanding of the Big Bang came from mathematical formulas and models, the evidence sent back by James Webb will unveil the deeper mysteries humanity has yet to uncover. Welcome back to our channel as we embark on a journey to decipher the latest evidence from James Webb. Big Bang and other theories. In today's rapidly changing world, humans grapple with countless existential questions that define our era. For instance, whom should I trust? What should I believe in? Does God truly exist? If so, how does God influence my life? Throughout history, from ancient philosophers to modern scientists, individuals have pondered similar questions about the origins and fate of humanity and the universe. Where do we come from? Where are we going? What is the purpose of this world? Or perhaps, as philosopher Bertrand Russell famously quipped, man is a feeble creature crawling on a tiny, insignificant planet with nothing significant about him. These questions have often left humanity and scholars alike scratching their heads, deeply engaged in contemplation to find answers. Because these queries cannot be easily explained through simple laboratory experiments. However, this doesn't mean it's a dead end in our quest for understanding. Numerous hypotheses and compelling answers, based on logic and reason, have emerged to address these existential puzzles about the origins of both humanity and the universe. Among them, the Big Bang Theory stands out as a particularly intriguing and worthy topic of discussion. Georges Lemaitre, a Catholic priest, was the first to propose and present the hypothesis of the Big Bang explosion. At that time, the Big Bang was likened to a great cognitive revolution because it seemed to have discovered, found, and rationally explained the origins of humanity and the universe. According to this theory, the Big Bang is a sudden and powerful event that created space, energy, and matter, the origin of the universe as we know it today. Long considered a speculative concept, recent advances in fundamental particle physics and observations of large astronomical structures have made it more consistent with the structure and complexity of matter in the universe and more widely accepted. In this scenario, the universe initially consisted of a dense and hot sea of matter. The Big Bang explosion occurred, and from then on, all other events and phenomena began. In the early stages, the universe consisted of objects such as electrically charged elementary particles, quarks, and antiquarks. Later, this soup became richer with lighter particles and antiparticles, collectively called leptons, including electrons, neutrinos, and their corresponding antiparticles. At a high temperature of about 10,000 trillion degrees Kelvin, the first heavy particles appeared, protons and neutrons, through the combination of quarks. The leptons then rapidly proliferated, eventually becoming the first atoms. However, as the universe expanded and cooled, leptons became less common. When the temperature dropped to about 10 billion degrees Kelvin, protons and neutrons began to combine to form deuterium. This moment occurred when the cosmic clock was only 1 second old, and the energy of the photons was still large enough to cause the first nuclear fission. By 3 minutes later, when the temperature decreased to 1 million degrees Kelvin, photons no longer had enough energy to break nuclear bonds. About 300,000 years after the Big Bang, the universe cooled down to below 3,000 degrees Kelvin and became transparent. Electrons no longer moved as fast as before and could be captured by nuclei, forming atoms and becoming the building blocks of the universe. Matter, light, and other forms of radiation filled the increasingly thin space as the universe expanded. Billions of years later, large gas clouds began to spread out, each cloud evolving into a galaxy. And then gravitational forces acted to form clusters of stars and star systems, while the universe continued to expand. Since its inception, many scientists have sought to provide evidence for the validity of the Big Bang timeline. In 1929, the Hubble Space Telescope first observed the redshift of the spectra of galaxies, indicating that they were moving away from us at a rate proportional to their distance. This suggested that the universe is expanding, and the space in which galaxies move together is also expanding over time. In 1965, Penzias and Wilson, USA, discovered the cosmic microwave background radiation, which has uniform properties in all directions and has a temperature response characteristic of a black body at about 3 degrees Kelvin. This is consistent with the Big Bang hypothesis. This radiation is a trace of the oldest light from the primordial universe. These are the first photons emitted after the universe became transparent, leading to the elongation of their wavelengths. From the 1970s onwards, scientists have discovered many light elements in the universe, including deuterium, helium-3, helium-4, and lithium-7, with helium-4 particularly constituting 25% of the total mass of the universe. This supports the hypothesis that helium was produced in the early stages of the Big Bang. However, with the advancement of nuclear physics and theoretical physics since the 1980s, two difficult remaining questions from the Big Bang have been explained: the absence of antimatter and the flatness of space. The sudden appearance of theories related to dark energy and dark matter has also led many to express skepticism about the very hypotheses developed based on the Big Bang. What's more, these hypotheses are gradually being challenged by evidence coming from James Webb. Strange galaxies. In an article published in the Arxiv Journal, astronomers from the University of Edinburgh, Scotland, have discovered what is believed to be the oldest galaxy ever observed by humans. It is located 35 billion light-years away from us, forming about 235 million years after the Big Bang. The galaxy is named Sears 93316, with a redshift of 16.7. In astronomy, this term describes an object emitting red light as it moves away from the observer, a consequence of the universe's expansion. A higher redshift implies that the observed object is farther away from us, and it formed earlier in the universe. The newly discovered galaxy is part of the Cosmic Evolution Early Release Science (SEERS) project, which utilizes the James Webb Space Telescope to search for the oldest objects outside our universe. Just a week prior, data from the $10 billion telescope enabled astronomers from Harvard University to discover Galaxy 13, a galaxy formed about 300 million years after the Big Bang. Not only Sears 93316, but the research team also observed another ancient galaxy named Maisie's Galaxy, with a redshift of 14.3, formed about 280 million years after the Big Bang. Sears 93316 is not the first case to astonish scientists. Back in 2022, when Webb was first put into operation and pointed toward the distant voids of space, the appearance of a myriad of peculiar monsters in the dark expanse left much of the public stunned. That was when the two ancient galaxies, Galaxy 13 and Z12, came into view. The stars in these galaxies are estimated to be about 300 million years old, post-Big Bang, and have masses equivalent to 1 billion suns, relatively small compared to galaxies in our Milky Way, which have a diameter of 100,000 light-years. At that time, these two galaxies were the prime candidates for the title of youngest galaxies ever detected post-Big Bang. However, not long after, the results from Webb were even more surprising. We have discovered nearly 700 galaxies similar to these, with lifespans increasingly closer to the birth of the universe. It was truly a colossal shock. Up to the present moment, the galaxies with the longest lifespans ever discovered by humans have continuously changed positions. Most recently, we have discovered additional new candidates. The second and fourth farthest galaxies ever observed were recently detected in an area of space called the Pandora Cluster, or Abell 2744, using data from NASA's James Webb Space Telescope. By tracking the deep field images of the region, an international team led by researchers from Pennsylvania has confirmed the distances of these ancient galaxies and inferred their characteristics using new spectroscopic data. Information about the emitted light across the electromagnetic spectrum from the JWST. At a staggering distance of nearly 33 billion light-years away, these extremely distant galaxies provide profound insights into how the earliest galaxies could have formed. Abell 2744. The first author, Bingji Wang, a postdoctoral scholar at Pennsylvania State University, stated, "There is very little information about the early universe, and the only way to learn about that time and to test our theories about the formation and evolution of galaxies is with these very distant galaxies." The Eberly College of Science at Pennsylvania State University, as a member of the JWST Uncover, Ultra-Deep NIRSPEC and NIRCam observations before epoch of reionization team, conducted the research. Before the analysis, they only knew of 3 galaxies confirmed at such extreme distances. Studying these new galaxies and their characteristics has revealed the diversity of galaxies in the early universe and how much there is to learn from them. Because the light from these galaxies takes so long to reach Earth, it provides a window into the past. The research team estimated that the light detected by JWST from these 2 galaxies was emitted when the universe was about 330 million years old and traveled approximately 13.4 billion light-years to reach JWST. However, researchers noted that the galaxies are currently about 33 billion light-years away from Earth due to the universe's expansion during this time. Joel Leja, an assistant professor of astronomy and astrophysics, as well as a joint appointee at the Institute for Computational and Data Sciences at Pennsylvania State University and a member of Uncover, stated, "The light from these galaxies is incredibly ancient, older than Earth by about 3 times. These primordial galaxies are like beacons, with light piercing through the very thin layer of primordial hydrogen gas that makes up the early universe. It is only through their light that we can begin to understand the strange physical mechanisms governing galaxies near the dawn of the universe." Notably, these 2 galaxies are significantly larger than the 3 previously observed galaxies at such extreme distances. One of them is at least 6 times larger, with a diameter of about 2,000 light-years. To put it into perspective, the Milky Way galaxy has a length of approximately 100,000 light-years, but according to Wang, the early universe is believed to be highly compressed, so it is quite surprising that these galaxies are so large. Wang explained, "Previously discovered galaxies at these distances are point sources. They appear as a dot in our images. But one of them seems elongated, resembling a peanut, while the other looks like a fuzzy ball. It's unclear whether the difference in size is due to the way the stars formed or what happened to them after they formed. But the diversity in galaxy properties is truly fascinating. These primordial galaxies are thought to have formed from similar materials, but they have shown very different signs." The 2 galaxies are among the 60,000 light sources in the Pandora cluster, discovered in one of the first deep field images taken by JWST in 2022, its first year of scientific operation. This region of space was chosen in part because it lies behind some galaxy clusters that create a natural magnification effect called gravitational lensing. The gravitational pull of the combined mass of the clusters curves space around them, concentrating and magnifying any light passing nearby and providing a magnified view behind the clusters. In a matter of months, the Uncover team has narrowed down 60,000 sources to just 700 candidates for further research, 8 of which they believe could be among the first galaxies. Subsequently, the JWST, James Webb Space Telescope, focused on the Pandora cluster, recording the spectra of the candidates, a kind of fingerprint detailing the amount of light emitted at each wavelength. Various groups are employing different methods to search for these ancient galaxies, each with its strengths and weaknesses. Our focus on this colossal space magnifying glass provides us with an incredibly deep window, but it's a very small window, so we're just rolling the dice. Some candidates don't yield convincing conclusions, and at least one of them is a case of mistaken identity, something much closer to mimicking a distant galaxy. Researchers also utilize detailed models to infer the characteristics of these primordial galaxies as detected by the JWST. As predicted by researchers, two youthful galaxies, low in metallicity, are rapidly evolving and actively forming stars. Leja explains, the first elements were formed in the cores of early stars through fusion processes. It makes sense that these primordial galaxies lack heavy elements like metals, because they are among the first factories to produce those heavy elements. And of course, they would have to be young and actively forming stars to become the first galaxies. But confirming these characteristics is a crucial test for our models and helps validate the entire framework of Big Bang theory. Researchers note that along with gravitational lensing, the JWST's powerful infrared instruments will be able to detect galaxies even farther away if they exist. They have a very small window into this area, and we haven't observed anything beyond these two galaxies, despite the capability of the JWST. This could mean that galaxies hadn't formed before that time, and we won't find anything farther out. Or it could mean they simply weren't lucky with their narrow window. This project is the result of a successful proposal submitted to NASA outlining how to utilize the JWST during its first year of scientific operations. In the initial 3 submission cycles, NASA received more proposals than 4 to 10 times the available observing time on the telescope allowed, and only a small fraction of those proposals could be selected. Leja's team was both thrilled and somewhat surprised when their proposal was accepted. It involved coordination, quick human action, and the telescope pointing at the same object twice, which was a significant demand for the telescope in its first year of operation. There was immense pressure as the team had only a few months to identify the target for observation. But the JWST was built to search for these first galaxies, and it's exciting to be doing just that at this time. Age of the universe. After a slew of ancient galaxies surfaced, the Big Bang theory was further subject to debate. A host of old issues were revisited for examination, most notably the question of the true age of the universe. If the laws of physics remain unchanged and quantum hypotheses are still accepted, then surely something has changed. It's either the Big Bang or our fundamental understanding. The universe is not necessarily older than 14 billion years. To have an older universe, we would have to discard the standard cosmological model, called the Lambda CDM model, that describes our current expanding universe. There are also other pieces of evidence suggesting a universe younger than 14 billion years. For example, the farthest stars and galaxies we see, which existed about 13.5 billion years ago, appear young and chemically immature, exactly what we would expect if we observed them shortly after their formation along with the universe. Data from the European Space Agency's Planck mission, collected from 2009 to 2013, suggests the universe is 13.82 billion years old. Another estimate, based on observations from the Atacama Cosmology Telescope in Chile, has reduced the age of the universe by a few hundred million years, yielding a figure of 13.77 billion years. However, astronomers at Cardiff University in the UK have indicated that the uncertainty in this measurement still aligns with the age determined by the Planck mission. Alternatively, if contentious measurements about the universe's rate of expansion are accurate, the universe could be younger. The uncertainty doesn't stem from our methods of measuring the universe's age being lacking. Rather, there are still aspects of the universe that we don't understand. How much older will the universe grow? Cosmologists are uncertain about what will happen. It all depends on the nature of dark energy, the mysterious force causing the universe's ever-accelerating expansion. If that expansion continues unabated, it could lead to the universe's end sooner than expected. In a big rip, where the fabric of space is torn apart, around 22 billion years from now. However, if dark energy weakens and the acceleration slows down or even halts, the universe may have an extended lifespan. If the universe continues to expand steadily or reaches a balanced state with gravitational forces pulling it back, it could exist indefinitely. After 2 trillion years, all galaxies beyond our local supercluster bound by their gravitational pull will vanish beyond the universe's observable horizon, where the universe is expanding so rapidly that even light cannot reach. In about 100 trillion years in the future, all star formation processes will cease. Around 10 circumflex 43 years from now, meaning 1 followed by 43 zeros, the protons inside atomic nuclei will begin to decay, signaling the end of matter as we know it. Eventually, after about 10 circumflex 100 years, called a googol, even supermassive black holes will evaporate. All that remains will be photons, neutrinos, electrons, and possibly dark matter. If dark energy somehow switches off, this could occur if it's a dynamic energy field known as a scalar field. Gravity might regain its attraction towards the fleeing universe and cause it to collapse into a big crunch. However, when this could happen is still unclear. What will we continue to discover soon? In the long term, we must continue to advance to step forward in uncovering the mysteries yet to be solved. The James Webb Space Telescope will continue to pursue the mission set out from its inception. This journey may extend even longer than the existence of Hubble, to search for light from the first stars and galaxies formed in the universe after the Big Bang. Study the formation and evolution of galaxies, understand star formation and planetary formation, and investigate planetary systems and the origins of life. Currently, Webb's activities are controlled through the General Observer (GO) program, the Guaranteed Time Observation (GTO) program, and the Director's Discretionary Early Release Science (DDERS) program. The GTO program provides guaranteed observing time for scientists who have developed hardware and software components for the observatory. The GO program offers all astronomers the opportunity to apply for observing time and will occupy the majority of observing time. GO programs are selected by the Time Allocation Committee, TALC, through peer review, similar to the proposal evaluation process used for the Hubble Space Telescope. We will continue to observe the birth of the universe while searching for civilizations beyond human understanding. Webb is just the beginning of a peaceful prelude to the massive waves of knowledge that will come to humanity in the decades ahead. We will systematically address lingering issues over many decades, encompassing both fundamental and advanced topics in cosmology. Initially, Webb will tackle macroscopic questions. How vast is the universe? What is the formation process of galaxies? Does dark matter and dark energy truly exist? And ultimately, where does the universe come from, and how old is it by now? These are all questions that have puzzled many scientists due to their uncertainty and macroscopic nature. Following that, we will continue to discuss the topic of extraterrestrial life. In the vast infinite universe, I believe we are not alone amidst the twinkling stars in the sky. Goodbye and see you again.